Because what we normally do when we have guests on is we always say, like, take us back, when did you first kind of get into your field? When did you first discover that this was the origin as like a passion? However, I think before we get to that, like, because we normally have people on who are kind of from linked or very similar fields to us. However, as you said, you work in paleomagnetism. So I think for ourselves and for the listeners, what is paleomagnetism?
Okay,
as the definition.
Yeah, it's a study of the magnetic field recorded in rocks, basically. Okay. And normally we're talking about Earth's magnetic field recorded in rocks, because most rocks are terrestrial from Earth. But you can have, lunar paleomagnetism. You can have meteorite paleomagnetism as well. So it is, it's just what it sounds like, ancient magnetism. So, most rocks, when they form, will lock in some sort of signature from the ambient magnetic field that they form in. So, and that's normally, on Earth, that's normally the Earth's magnetic field, because that kind of dominates over everything else.
And then you can kind of track how that changes through geological eras.
Yeah, so then it maps into geomagnetism, which is the study of Earth's magnetic field. In particular, it's so the magnetic field's been around for a very long time, and it changes on timescales that are longer than human timescales. So our only chance of really understanding it is to look to the geological record, and these kind of, we've got direct measurements going back, a few centuries from, mariners and things, but that's, if you were to compare the magnetic field to the sort of climate system, then, a few centuries, the magnetic field is like, just a few weeks or something for the climate.
Very little happens.
So you can't, you couldn't study the climate, in just a few weeks of data. So you need these thousands and millions of years long records.
So they almost hold like ancient transcriptions of the past, like almost information is interlocked in basically rocks.
Yeah, I mean,
through magnetic fields,
and that's that's true about rocks in general. The whole field of geology is like using rocks to tell you about the ancient Earth. But the special thing about paleomagnetism is that it's telling you about the magnetic field, which has its origin in the Earth's core and is relatively unaffected in its passage from the Earth's core, 2,900 kilometers beneath our feet, all the way up to the surface. So it's like you're getting a record of what's going on in the deep interior of the Earth, and that isn't something that generally, geology can give you. It's only telling you about the surface processes.
So it gives you a more deeper understanding of what was going on right in the center of our planet, essentially.
Yeah, that's right.
So cool.
And to understand, the kind of evolution of our planet, then I think paleomagnetism is like essential.
You say it's the magnetism trapped in rocks. So what specifically are you looking for in, like, is it just the magnetic field that the rock gives off, essentially, or is there certain features?
Yeah, it is basically. So most rocks are magnetic to some degree, and because they've got tiny little magnetic particles in there. So, the most famous of them is called magnetite, and it's just an iron oxide, and it forms about 1%, of basalt, which is the most common rock on the Earth's surface. So underneath all the oceans is basalt, basically.
Okay.
And that 1% of that basalt is magnetite, which is really strongly magnetic, but just tiny little grains, because big grains are unstable. They don't record a reliable record. They will have their record constantly overprinted. Whereas really tiny ones, so we're talking, sub-micron here, more than thousandths of a millimeter, less than that. They're the most stable.
Larger rocks are more unreliable because there's
larger grains within the rocks.
Larger grains are more unreliable.
Yeah.
We've just had a grain expert on, haven't we? Dr. James Baker.
Yeah, in like granular flows. And that was his expertise, and how things
grains compact, on volcanoes
and
and
like
stuff.
volcanoes and
like
emergency stuff and that. So very similar. Like, it's weird.
No, sorry.
It's a bit.
I guess rocks are granular on all these different levels. So it's it's like fundamentally rocks are collections of minerals, which form themselves into what we call the grains or the crystals. So they've got to be small to be reliable. recorder.
Makes sense.
What is then, Andy, for you, like, what is the most important like thing that paleomagnetism brings us about possibly making predictions about the future or looking into the past? What is the most important like application of it? It might not be the stuff you do, or is it the stuff you do? I don't know.
Well, it's related to the stuff I do, yeah. So as I said, the magnetic field is always changing, right?
Yeah.
And it does change a bit on human timescales, you know. So if you're into hiking at all and you want your compass to be, you know, dead accurate, then, you know, every few years or so you should slightly modify it because magnetic north will have moved relative to geographic north, right? So it's doing these small changes all the time, and most of the time, you know, magnetic north is near geographic north, right? And it's sort of just dancing around. But then every now and again, this, what we call this secular variation, this just sort of wobble of the magnetic field, it gets out of hand, and the field can collapse altogether. And you might have heard of magnetic reversals, the polarity flips. Yeah, that's right. Yeah, so that's the most extreme example of that. Then that the field becomes so chaotic that then when it rebuilds, it forgets which polarity it was originally in, and it just grows back in the reverse polarity, and then it gets stuck